Hello, welcome to my presentation on essentials of indicating instruments. I am Swati Polasa, lecturer in Electrical and Electronics Engineering, Sanjay Gandhi Government Polytechnic, Adilabad. Let us have a look on a first slide, requirements of indicating instruments. Indicating instruments are those which indicate the value of quantity that is being measured at the time of measurement. This clearly says that the indicating instrument will indicate or show the value of the quantity that is being measured only at the time of measurement. That means when signal is removed, it is not going to show the correct value. It is going to show either 0 or something like that. Such instruments essentially consist of a pointer which moves over a calibrated scale and which is attached to a pivot bearing moving system. The moving system is subjected to following three torques. Number 1, it is a deflecting or operating torque. Number 2, a controlling or restoring torque. Number 3, a damping torque. Now here, we should understand that we are going to have some system, and this system is going to have a pointer attached to it, and this pointer will be moving in a circular direction as shown, and the pointer should be pointing to some value, and that values are mentioned in a calibrated scale. So this is the calibrated scale that we are going to see. So it is being mentioned here. So this is where it is mentioned. Instrument essentially consists of a pointer. So this is the pointer which moves over a calibrated scale, and this is the calibrated scale. Now this moving system should have some support so that it can move freely. So this moving system should have some support so that it can move freely. And that support system, we have different types, and one of those types is pivot bearing moving system. Now, we are trying to learn about the essentials of indicating instruments. First thing is the pointer should move so that it can show some value. So for that pointer to move, this moving system should have some torque. It should have some force acting upon it so that it will have a twisting force so that it can rotate. So that particular torque is what we call as deflecting torque. And deflecting torque is caused because of different effects. We will see it later on. So that is what is a deflecting torque. So the torque with which pointer will start moving. Now then we will see about the controlling torque. So controlling torque will oppose the deflecting torque. So our deflecting torque is in the direction shown here. The controlling torque will oppose the deflecting torque, so it will be acting in opposite direction. And then now, because we have two torques acting upon this pointer, actually it is acting on the moving system and thus the pointer. So when you have two, then you will be having a to and fro motion. And that to and fro motion is what we call as oscillations. And to stop the oscillations or to damp down the oscillations, we require another torque so that the pointer will come to rest quickly. And that torque is what we call as damping torque. In this way, we have three torques acting upon a moving system so that we can take the readings in a short duration, less time. So we'll go to our next slide, which explains briefly about deflecting torque. As we have seen in the earlier slide, the deflecting torque causes the moving system of the instrument to move from its zero position. The method of producing the torque depends on the type of the instrument. It is produced by making one of the following effects. It is trying to use one of these effects. So to produce the deflecting torque, instrument can use any of these effects. So first one is magnetic effect, heating effect, chemical effect, electrostatic effect, electromagnetic induction effect of current or voltage. Then we'll go for controlling torque. As we have seen that pointer will start moving because of deflecting torque, and when it moves, the movement is going to be indefinite. So the movement is going to be indefinite. So we have to stop the movement of the pointer or the moving system. For that we require controlling torque. So the controlling torque will oppose the deflecting torque. Now how should be the property or characteristic of the controlling torque? It should increase with the increase of deflection. That means it increases with increase in the deflection of the moving system. Under the influence of the controlling torque, the pointer will return to its zero position on removing the source producing the deflecting torque. As we have seen here, this is the moving system. This is the pointer, and say the calibrated scale is this. This is our display. And here say we have two terminals to connect the meter to the external circuit. Okay. Now this is the calibrated scale. So let us start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Say the scale is not uniform. It is showing something like this. Now when the deflecting torque is applied, pointer will start moving in this direction. This is because of deflecting torque. The pointer will show some deflection. That means your pointer will change its position from 0 to some value. So it will start from 0, 1, 2, 3, 4. Because deflecting torque is acting on it, it will just start moving. Okay. If if there is no controlling torque, the pointer will go on moving. So what we have to do is, when it is just moving, that means it will rotate like this. This is what we say indefinite motion. It is not definite that the pointer will stop somewhere, so that we can take some reading over it. So for that, there should be some torque which opposes the deflecting torque, and that torque would be controlling torque. So now when the pointer was showing 0 before applying any source of deflection, now after applying some source of deflection, say we are trying to measure the value of current. Now I'm giving the quantity to the meter. Then the pointer should be moving. Now, say we know the true value of the current, it is 2 amperes. So pointer should stop at 2 amperes. It should stop at 2 amperes. We are expecting that it should stop at 2 amperes. But without controlling torque, it cannot stop at this position. What it does is it will go on moving. So to stop at this position, we require another torque which opposes the deflecting torque, that acts in opposite direction of the deflecting torque, and that torque is what we call as controlling torque. So you can see that deflection torque is acting this way, controlling torque is acting this way, and the pointer is stopped at 2 at this position. Why? Because at this position our deflecting torque is equals to the controlling torque. And this is what is going to happen in the meter. Now more is the deflection torque, more will be the controlling torque, so that the pointer will come to a state of rest showing some value. Now if deflection torque is 0, say the deflection torque is 0. Now pointer should come back to 0 position. That will happen only when controlling torque is there. So when controlling torque is there and deflection torque is 0, your pointer will come to which position? It will come to 0 position. So it will come to 0 position this way. So this is how our controlling torque will oppose the deflecting torque. So we'll see different types of how can we produce the controlling torque. So controlling torque is produced either by spring or gravity control. So we have spring controlled instruments and we have gravity controlled instruments. So first we will look into spring control measuring instruments. In this type of measuring instruments, we are going to have a hairspring. The hairspring is very thin, it occupies very less space, so it is attached to the moving system. Hairspring is attached to the moving system, so it exerts controlling torque. Let us see how. Here you can see a picture. This is the moving system. You can see that moving system is having some coil and there is a stick-like structure. This stick-like structure is what we call as a spindle. It's made up of steel, mild steel, and this spindle needs a supporting system. You can see that there is a conical end to this spindle, and this is what we call as a pivot, and it is being this is what is a supporting system. Here you will have a dual bearing. So this is a dual bearing pivot system, and now you can also see that there is a spring here. Spring obviously should be having two terminals. We can see that spring will be having two terminals. This is a spring. So here you have two ends of this spring, end A and end B. How this is connected here, we'll see. This end B is here. End B is having a rigid contact with the spindle, and end A is connected here. Okay, so here you can see in this picture, we have another picture here. Here it is pretty clear that you have two springs here. Here in this picture we had only one spring, and here you can see two springs here. So one is attached to the moving system and another one will be going out of the system to the terminal, and here we have another B spring here. So we'll see what happens when pointer is deflected. One spring unwinds itself while other is twisted, which means that the two springs are wound in opposite manner. Both of the springs are wound in opposite manner. Say our deflection is clockwise, then if A spring is getting unwind, then B spring is getting twisted. That means here we have more tension in the spring. Here we have less tension in spring. This is getting unwound and this is getting twisted. So this twist in the spring produces restoring torque, which is proportional to angle of deflection of the moving system. More is the angle of deflection, more will be the twist, so more will be the restoring torque. So this is how we have our control system, spring control system. So let me explain you why do we require two springs when single spring can do the job. The reason behind it is basically there are two reasons, important reasons. First important reason is this spring are used to complete the circuit. Suppose in this spindle we have a coil, say. Coil will be having two ends, these two ends. So one end is connected to spring A, another end is connected to spring B. So coil will be moving. Because of coil movement, you will have the spindle moving, spindle, and the coil end is attached to the spring, a rigid contact, so it is moving, but the other end of the spring, it is not moving, it is giving to the end terminals of the meter box. As I said that meter box will be having two terminals from where you can connect it to external circuit. So this is connected to the other ends of the spring, and inside the coil should be moving, so that is connected to these ends of the, let me name the ends, say this is XA and this is XB, and this is YA and this is YB. YA and YB are projected outside this manner, and XA, XB are connected to the coil inside the moving system. So for that purpose, two springs are useful. And second reason, so first thing is to complete the circuit, close the circuit. And the second reason is because of different temperatures, we will not have same temperature conditions throughout the year. So in summers, the spring is subjected to high temperatures, because of which there will be slight changes in, there will be expansions in the spring. So because of the expansions, if you use one spring, the controlling torque will be differing. Now, if you have two springs which are wound in opposite manner, then the effect of expansion or contraction, expansion in hot temperatures, contraction in cold temperatures, both of the springs will get cancelled out. So we are actually neutralizing the temperature effects by having two springs. So this is the another advantage of having two springs. Hope I'm clear with this slide. Keeping that in mind, I'm moving to next slide. The other one, then we'll see the essential requirements of the spring. So first important requirement of the spring is they should be non-magnetic material. They should be proof from mechanical fatigue. Of course, spring material should not have a mechanical fatigue nature. Now, where springs are used to lead current into the moving system, the one which I have explained in the previous slide, they should have low resistance temperature coefficient. So the mostly used or widely used spring is phosphor bronze. Phosphor bronze has been found to be the most suitable material for hairspring. For flat spiral spring, the controlling torque developed by deflection is given something like this. So this is the controlling torque. It is given as E, which is Young's modulus of the spring material, into B. D is the width of the spring. Because it's a flat spring, see, it is going to be something like this. So like this. So width of the spring, this is the width of the spring, length of the spring. So this whole thing should be length of the spring, and this should be width of the spring, and theta is angular deflection of the pointer of the moving system. And keeping these variables, we come to a formula that controlling torque is equals to EB T cube into theta by 12 L Newton meter. So Young's modulus, thickness, width, width of the spring and length of the spring are not going to get changed for a measuring instrument. So they can be just considered as constant. So I can simply replace that TCZ is proportional to theta. So controlling torque for a spring control measuring instruments is proportional to angle of deflection. So there is every possibility that we have uniform scale of the display. So when we have seen that there will be a graduated scale on which the pointer will be moving, over which the pointer will be moving. So this scale is going to be uniform. So this is what uniform, the distance of readings is same. So this is a uniform scale. Now we'll go for a gravity control. measuring instrument. In a gravity control, a small weight is placed on arm attached to the deflecting system. The position of this weight is adjustable, which means that to the moving system, we are going to attach a small weight which is trying to bring back the pointer to its original position because of gravity. So this is the idea. So the position of this weight is adjustable. We can adjust where to place the weight and all. This weight produces a controlling torque due to gravity. And this weight is called as the control weight. Another adjustable weight is also attached in the moving system for zero adjustment and balancing purpose. For all the system to remain in a balancing purpose, not to tilt, there will be another weight which is attached. It is called as balanced weight. We will have a look on the picture of the gravity control. Please go through the picture here. So this is a gravity control measuring instrument. This is our plan of the spindle, top view of the spindle, and this is our pointer which is trying to move over the graduated scale. And to this spindle we have weights attached. This is the control weight which is trying to pull back the pointer to its original position, and this is the zero adjusting or balancing weight which is trying to balance the positioning of balance the spindle and also trying to bring back the pointer to zero position. This is what we call as, so this is the balancing weight. This is the control weight. Now let us see how it works. This is the position of the spindle, and here is where the controlling weight is applied. So from center to the weight, say the distance is L, and this is how gravity works. And actually it was in this position. This is the standard position. Now when pointer is moving in clockwise direction, your weight also moves in clockwise direction. So this particular situation is mentioned here. You can see that, say the pointer is moving through an angle theta, the weight will also move clockwise through an angle theta, and that is mentioned here. Now the weight, coming to this picture, the weight already moved through angle theta. Now we'll see what are all different forces that are trying to oppose the movement of the pointer. So here the weight should be downwards. So W is the weight that is applied, weight force which is applied in downward direction. Deflection torque is in the direction shown here, clockwise. Now what force is trying to exactly oppose this deflecting torque? Let us see. Now weight is downward direction. This is angle theta. Now if you break this weight force to two orthogonal components, so we see that this is W sine theta and this is W cos theta. So the force that is trying to oppose the movement of the pointer is W sine theta. So the controlling torque, this is the force. Torque is force into distance. So force is W sine theta. Distance is L. So the controlling torque will become W sine theta into L. So we can see that this vertical line and the line of force of gravity pull or weight both are parallel, and this is the line joining the center and the weight. So this angle is also theta. So if this is the weight acting downward direction, we can split it into two components. This is going to be W cos theta and this is W sine theta, and the force that is quite opposing the reflecting torque is W sine theta. So the torque, controlling torque, can be expressed as the force which is opposing the reflecting torque into distance, and that distance is L. So this F opposed is W sine theta, and that is what is mentioned here. So the controlling torque is WL sine theta. Weight of the control weight is not changed until we open the box, so it is constant, and L is the distance from center, it is also constant. So W into I is a constant, so we can say that TC is proportional to sine theta. Unlike the spring control, we had TC is proportional to theta, hence the scale was uniform. But coming to the gravity control, TC is proportional to sine theta, so the scale is non-uniform. Hence, we have seen two different types of controlling torques. Now let us see damping torque. The pointer will try to occupy a position of rest when two torques are equal and opposite. However, due to inertia of moving system, pointer will come to rest immediately but oscillates about its final deflected position. So you just think about my spotlight. Say there are two forces acting on the spotlight. One is right direction and another one is left direction. So when these two forces are equal, my pointer will come to state of rest, but before coming to state of rest, it will just try to oscillate and then it will come to state of rest. So this is what will happen to the pointer also, pointer in measuring instrument. So to overcome this difficulty, a damping torque is to be developed by using a damping device attached to the moving system. So to bring the pointer to a stable position as early as possible, we require damping torque. We will see how the damping torque acts. So the damping torque is actually proportional to the speed of rotation of the moving system. If the deflection torque is less, obviously controlling torque will be less. So the deflection torque is less, hence the speed of rotation will be less. If the speed of rotation is less, damping will also be less automatically. But if speed of rotation is more, then damping torque will be more. So we say that the damping torque is equals to rate of change of deflection, d theta by dt, rate of change of deflection, or which we call as speed of rotation. Okay. So d theta by dt is speed of rotation of the moving system. So we can have different types of dampings actually in a system. So you can see that this is the final deflection, which is theta, and this is the time taken to arrive into a final deflection. So say this is a point where the pointer should stop. So the pointer should actually travel through angle theta and it should stop changing the angle. It should stop. It should come to stop position, showing some reading after rotating through angle theta. Now we'll see what happens. So there we have seen that there are going to be around 3 different types of damping torques. So first type of damping is the pointer will quickly move. It will quickly move. Instead of stopping at theta, it will move to the value more than theta, and it realizes that the controlling torque is high, and hence it will come back to theta, and the controlling torque was so high that it reduces the theta value, deflection value, to less than theta, and then again it realizes that deflection torque is more than the controlling torque, hence deflection will increase. So how it actually look is, so this is our center, this is 0, and this is theta, say, where our pointer should stop. Now the pointer was initially at 0. Now I have applied some signal to the measuring instrument, so deflecting torque will act on it, so the pointer should be moving. Now for as the pointer is moving, as deflecting torque is more increasing, controlling torque will also increase. Now pointer should actually stop at theta after traveling through an angle theta. But what happens is, in underdamped system, pointer will quickly move and it will come like this. I hope you're clear. I'll show it once again. For underdamped system, pointer will start moving from 0. It will quickly reach to a final deflection angle, and it will go beyond deflection angle. It will come back, and it will come back behind theta, and it will go beyond theta, behind theta, and it will come to rest. This is what we call as underdamping system. And coming to overdamping system, for the overdamping system, what happens is pointer will start from 0. It will go in a lethargic manner, slow manner. Slowly it will come to some value which is beyond theta. That means more than theta. A bit more than theta. But it will reach the value theta, but it is going to take a lot of time to reach the value of theta, final deflection. There is another type of damping which we call as critically damped. In this critically damped system, our deflection is going to start from 0 and it will come to final position as early as possible. So out of these 3 different damping systems, we would prefer critically damped system. So we'll see what are different ways to produce the damping torque. The damping torque is produced by following methods. First one is air friction damping. The other one, fluid friction damping. Third one, eddy current damping. Fourth one, electromagnetic damping. The working of eddy current damping and electromagnetic damping both are same, except where we use it, the damping torque is distinguished. Now we'll see how air friction damping works. Before going to that, we'll just go to the construction of this air friction damping. There are two types of air friction damping. Here, air friction damping is also called as pneumatic damping. Here we have shown two types of air friction damping. This is the first one. In this arrangement, you can see that there is a chamber here. This is what we call as air chamber. This is the center, and you have a pointer here. This is pointer, which will be moving over a calibrated scale. And to the spindle, we have a piston attached, and this piston is supposed to move inside air chamber. And this is the arrangement. And if you go for another type of the air friction damping, here what we have is, this is the spindle, and spindle is attached to a vane, and this vane is inside the air chamber. So when spindle is moving, not only pointer moves, we have another vane which is moving inside the air chamber. Here in this case also, when spindle moves or pointer moves, spindle will be moving. So when spindle moves, piston also moves inside the air chamber. When spindle is moving in clockwise direction, piston movement will be this way. When spindle movement is in counterclockwise direction, now the piston movement will be in counterclockwise direction. Now what happens inside the air chamber? Let us see. The clearance between piston and chamber walls is uniform throughout and is very small. So inside this chamber, the clearance is uniform throughout. It is very, very small. Now, when there are oscillations, the piston moves into and out of air chamber. So in this case, when there are oscillations, here there should be some oscillations. So when there are oscillations, that oscillations holds good inside the chamber. So the piston will also try to oscillate inside the air chamber. But inside the air chamber, there will be opposition to the motion as the air inside the air chamber gets compressed. So when piston is moving in clockwise direction, the air is compressed, which will try to oppose the movement of the piston. Now when it is counterclockwise, air here will get compressed. Again, there will be opposition to the motion of the piston. So this is how damping is produced. Coming to this type, so when your vane, or when the spindle is moving in clockwise direction, air in side 1, say this is side 1 and this is side 2, air in side 1 will get compressed, which will try to oppose the movement of the vane. And when the piston is moving in anti-clockwise or a counterclockwise direction, air in side 2 will get compressed and it will try to oppose the movement of the vane. So this is how it works. Coming to the fluid friction, it is similar to air friction, but instead of air, we'll be having oil. So because viscosity of oil is greater, the damping torque correspondingly is high compared to air friction damping. So when the moving system moves, we'll see how it is organized. So this is a suspension type. You have, this is the spindle. To spindle, we have a disc attached, and this disc is dipped in a oil pot. Now, how it looks is this. This is how, this is the plan. So this is the disc. This is the oil pot. Now, when the spindle is moving in clockwise direction, because of viscosity of the oil, it will not allow free movement of this vanes of the disc. Hence, it will try to oppose the oscillation. Clockwise or counterclockwise, logic is the same. Now let us see the eddy current damping. First, we will go to the arrangement of this eddy current damping, how it is arranged. It is shown in the picture clearly. This is the spindle, and this is the pivoting system. This is the spindle, and we have a pointer attached to the spindle. This is the damping system. In this damping system, what are all different parts we have? We can see some disc here. This disc is made up of aluminium. This is aluminium disc. And we have a magnet, another magnet, a small magnet, which we call as a damping magnet. This is one arrangement of eddy current damping. In this arrangement, we have a disc attached to the spindle, and we have a damping magnet where we can see that the magnetic field of the damping magnet is trying to cut the disc. This is the arrangement, one arrangement. We will try to understand the principle of this eddy current damping with this arrangement. Say our pointer, or say a spindle is moving in a counterclockwise direction. So the disc should also rotate in this manner, and the disc is made up of aluminium, and aluminium is a conductor, and you can see that there is a damping magnet here. There is a magnetic field. So when a conductor aluminum disc is moving, it is like a conductor moving in a magnetic field. So when a conductor is moving in a magnetic field, it cuts the magnetic field. So when a conductor cuts the magnetic field, so obviously it is changing. So when because it is moving, the conductor will be cutting, changing flux. So there will be EMFs induced inside the aluminum disc. So when a conductor moves in a magnetic field, an EMF is induced in it, and because the EMF is induced in a aluminum disc, EMF will find lot of closed paths. So there will be small amount of currents flowing in the aluminum disc, and those currents are called as eddy currents. So we'll be having small circulating currents, which we call as eddy currents inside the aluminum disc. What is the source of this current? The source of the current is the magnetic field, and another source of the current is movement of the aluminum disc. So the induction of the EMF is because of Faraday's law, and there, because there is closed path, currents are flowing, and the currents, we call it as eddy current, and this current interacts with the magnetic field to produce a electromagnetic torque which opposes the motion. So the eddy current will interact with the magnetic field, and it will try to oppose the motion of the disc. When it is trying to oppose the motion of the disc, it is ultimately trying to oppose the motion of the spindle. That means it is trying to oppose the motion of the pointer. So this opposition is only while oscillating. So the current is proportional to EMF, which in turn is proportional to the velocity of the conductor. Thus, if the strength of the magnetic field is constant, because we won't be changing the permanent magnet, so it is going to be constant. The torque is proportional to velocity of the conductor. That means position of the spindle, motion of the spindle. So for this, there is another arrangement. So this is arrangement 1. There is another arrangement of the eddy current damping shown in the slide. And here you can see this is a north pole and you have a south pole here. There will be a magnetic field from north to south. And here you have aluminum former. So this is some coil in a measuring instrument. And here you can see a metal former. This is a metal former on which you have coil placed, something like that. So this metal former will act like a conductor. So in this metal former, you will have eddy current produced, and finally you will have opposition to motion of the spindle. Hope you are clear with the eddy current damping. Now we'll look at electromagnetic damping. It is same as eddy current damping, but it is very particular when we discuss about galvanometers. So here what happens is the movement of the coil in magnetic field produces current in the coil which interacts with the magnetic field to produce torque. The torque opposes the movement of the coil and slows the response. It is the same. The magnitude of the current, hence the damping torque, is dependent upon the resistance of the circuit. Because if resistance of the circuit is high, the magnitude of the current is going to be less. If the resistance is less, the magnitude of the current is going to be more. More is the current, more will be the damping torque. This is how. So the electromagnetic damping is used in galvanometers. Now we'll have a look on the support of the moving system. The moving system should have following properties. One is the moving parts should be light and the frictional force should be minimum. Moving system should be supported by a fixed system. So there should be a flexible connection and frictional less connection between a fixed supporting system and a moving system. So what different types of supports we can have, how many types we can see here, mentioned as suspension type, taut suspension type, and pivot and dual bearing support. First, we will look into suspension type. Suspension type simply looks like this. This is saying our moving system. And here you will have a magnet, here you will have a magnet. Because of some effect, say, this should move. There is a torque developed in it and it should actually rotate. So for that you will have something like this. What we'll try to do is we will try to hang it here. We will suspend this moving system with the help of a fine ribbon-shaped metal filament for the upper suspension and the coil of fine wire for the lower part. So the ribbon is made up of spring material like beryllium copper or phosphor bronze. So this is a ribbon. And this is a wire. So this is suspension type support system. We'll go for taut suspension. For taut suspension, this is a type of in this type of suspension, we have flat ribbon suspension both above and below the moving system. So here you have a ribbon suspension. Here also you have a ribbon suspension. They are kept under tension by spring arrangement. So this is a um, this is fixed and this is fixed, and you have the moving system attached to these fixtures with the help of suspension ribbon, suspension ribbon and suspension ribbon and spring tension. So both the suspension type, we have it only in vertical position. So we should be using the instrument only in vertical position. Otherwise, gravity will change the position of the moving system. The moving system will face some other problems to move. Now we'll go for pivot and jewel bearing. This pivot and jewel bearings look something like this. So this is the spindle. So what happens? The moving system is mounted on spindle made of hardened steel. The two ends of the spindle are made in a conical shape. So you can see this is the conical shape and it is polished. So they form a pivot. So here we pivot. Similarly, other end of the spindle is also made in the similar shape. So that is also pivoted. You can see this is here the spindle, one end of the spindle, it is made into a conical shape and it is polished to form a pivot, and these ends fit in a conical hole. This is a conical hole, and in this conical hole we place a jewel so that there will be less friction interaction between pivot and the jewel. So friction will be very less. So these ends fit in a conical holes in a jewel located in a fixed part of the instrument. So this is a fixed part of the instrument. Similarly, you will be having the fixed part on the other side of the spindle too. So these jewels are preferably made of sapphire to form bearing. So here you have a jewel. This is a jewel. You can see this is a jewel. And here you can see two different types of bearing. This is a jewel bearing. This is a pivot and this is a jewel. And this is the contact surface between pivot and jewel. At this point, because surface contact is very less, jewel surface will be smooth, friction is automatically will be less. And here you can see that there is a spring between jewel and also a fixed part of the instrument. Here the jewel is embedded in the fixed part, but here there is a flexible movement between jewel and the fixed part. So this spring will increase the life of accuracy of the instrument. Why? Because it will reduce the error, systematic errors, as when we have a spring here, there won't be no wear and tear at the point what I am showing here. At this point, the contact uh, point, because the pivot will be moving, there will be small wear and tear here. It that situation is reduced with the help of spring, because it when weight is more, it will be coming back and forth. So the contact of the pivot and the jewel is not that rough that the wear and tear is easy to occur. So this is how we have different types of support system. So the optimistic learning outcomes of this presentation expected to be the state of, after completion of this presentation, the listener should be able to state the purpose of obtaining deflecting, controlling, and damping torques in indicating instruments. And they should be able to explain the methods of obtaining deflecting torque, controlling torque, types of controlling torque, and damping torques in indicating instruments. And they should be able to state different supports of moving systems. Thank you.